Hi all. I want to do as a review of concepts that many of you have seen in other classes, but may not be feeling very comfortable with. Just a short reminder on some of the important things that we need from logic, and specifically focusing on those things that are relevant for analysts. So a little bit about logic. Logic consists of statements. And statements for us, they are things like x is bigger than 2, or I am from Europe. These are claims that are either true or false. And from the perspective of so-called propositional logic, we will think of these as just single statements. So sometimes these are called atomic statements, and these statements are called propositions, and the relationships between propositions and how logical conclusions can be drawn from them is called propositional logic. Now, single propositions are not interesting as the combinations that we can form from them. So and is one standard example, and it's denoted symbolically. If we have two propositions A and B, it's denoted by A wedge B, and it's read A and B. For example, x is bigger than 0 and x is less than 1, which usually means another way of writing x is inside the open interval 0, 1. So if you have a truth table, now the way of representing the truth of such statements is by listing the possibilities for A and B, and then indicating the outcome. Here, 1 means true, and 0 is the case where the statement would be false. Because there are two statements, there are 4 possible combinations of these truths. Either both are true, in which case A and B is true. But if either one of them is false, or if both of them are false, then the claim is fully false. Now, another connective, as these are called, these operations, is OR, and it's denoted by a opposite wedge, A, B, B, and it's read often A or B. And for that, the truth table, as say the statement x is bigger than 0, or x is less than -1, which would normally be written as in interval notation as up to -1, union 0 to infinity. So here we're already seeing in these examples how these connect with real analysis, in that many sets that we write actually include and or in their definition. So, but or means that one of these is sufficient. One of these claims is sufficient. So if we have a true statement in one of the sides, either A or B, we get true. But if both of them are false, that's the only case where we get a false statement. So these are relatively familiar. Now, the most complicated one, and the one where people make the most mistakes, is the implication. If A, then B, and it's written symbolically as A implies B, and can be read as A implies B. But also if A, then B, or A is sufficient for B. These are other ways of stating this claim. And an example of a true statement is x bigger than 1 implies that x squared is bigger than 1. But for implications, it's also if x squared is negative, then x is equal to 0. These are both true, even though the second claim of these seems nonsensical. And the way to understand, one way to understand this is that an implication is a promise. Whenever the assumption is true, the assumption is true, then the conclusion is true. But if the assumption is never true, then there's no cases that we need to be concerned about. So x squared, at least if our domain is real numbers, is never the case, then we can say anything on the other side because the condition for this contract is never true. A nice example that some students of mine have given is that if I have $1 billion, I'll buy you a Lamborghini. I don't have $1 billion and I don't expect myself to get that in my lifetime. So I'm safe to make that promise to you. And I can say that that's a true statement, even though it doesn't mean anything because the condition is never satisfied. So how does that that translates in the truth table is that whenever A is false or the assumption is false, we automatically get that the implication is true. It's only when A is true that we start implying something about the conclusion. So if A is true, then B must be true, and that's when we get a true implication. And in cases where A is true but B is false, that's when we get a false statement because our assumption is true but our conclusion is not. And a different statement that's closely related, that is often used in statements of real analysis, is A if and only if B. And it is better understood perhaps by its truth table. It gives the same value when it gives a true statement when both of them agree on the true, but it gives a false statement when either of them fail while the other one is true. So they have to share the truth values in order for this statement to be true. So this is expressed here. Equivalent means that they have the same truth values in all possible cases. So, for example, x bigger than 0 and x bigger than 1, this statement let's try it differently. X bigger than 1 is equivalent to x squared being bigger than 0 and x being positive, x squared being bigger than 1 and x being positive. X squared bigger than 1 is not quite sufficient for x being positive because it could also be less than -1. But if we also enforce that it's positive, then these two claims become equivalent. Now, equivalencies are very useful in logical deductions because they allow us to turn one statement into its equivalent form. And this is often written as a shorthand notation, A is equivalent to B, which means that for logical purposes and deduction purposes, we can interchange between A and B whenever we want. For example, these two statements, we can always convert them to each other if we have established one or the other as true. Now, one place where we get a lot of these implications and a lot of these connectives come is set theory, and that forms the foundation of real analysis. And one is the subset relationship between sets. And the subset relationships means, colloquially, that every element of A is also an element of B. Another way of saying it is that if X is in A, then X is also in B. So by stating it this way, we see that our condition of subset relation, and if we want to actually prove a subset relation, then we actually have to prove an implication. And this is common. They're very common. Many conditions in analysis take the form of implications. And therefore, many of the proofs have a similar structure. If we are proving an implication, we have to first assume A. Because the implication is only a promise assuming that A is true. It doesn't say anything about the cases when A is false. So we start the proofs, therefore, by assuming that A is true. That's the first fact that we can use. Then we can use logical deduction and any other assumptions that may be given to us in that context to hopefully then conclude B. So at the end of such a proof, we should be able to plainly conclude that B is true, or B, or some equivalent version of it. So often, and this is where the equivalences come, is it makes sense to try to turn your statement, change your statements into some equivalent form. So for example, just a simple example of one real variable analysis. If we want to show that 1 to infinity, the half open interval, is a subset of all the real numbers, such as square is bigger than or equal to 1, well, what we start from is writing this as an implication. And in proving that, we start by assuming that y is inside 1 to infinity. This is our assumption. And often this is written as fix y in this interval. If you want to emphasize that it's arbitrary, you can say fix y in that interval arbitrary. Then you deduce from it. So you massage this condition into forms that become more useful. So here it's useful to write that this implies, or it's equivalent to, y bigger than or equal to 1, because that's the definition of that interval. All the numbers that are bigger than or equal to y. Because y is bigger than or equal to 1, then by properties of inequalities, we know that y squared is bigger than or equal to 1. And here we would have to use some properties or lemmas. But here, this is very commonly accepted that this is true. So certainly one could find axioms that guarantee that. And we believe that that step is easy, and therefore that's an allowed step for most of the time. So now we have y squared is bigger than or equal to 1, but this is the membership condition of that set. So therefore, this is the same thing as saying that y is inside the set of all the elements whose square is bigger than or equal to 1. And this is now just an equivalent form of what we said before. And this is the proof. So it starts from the assumption, it uses a logical deduction and gets to the conclusion. Of course, most of the time, your steps will be somewhat more complicated than this. Now, what really gets real analysis or puts real analysis into life is quantifiers. Usually you don't have statements that are depending on an x, just an x, arbitrary x, or they are not just closed statements, but they have a context, a set that we are looking at, and they have quantifiers that indicate whether we say that the statement that depends on x is true for all x, or whether it's just true for some x. And one thing I will say about proving these is that for all x, again, we will have to think fix x and then conclude that px is true. Indeed, a different way of writing it for all x, px is true, is that if x is an A, then px is true. So this is basically the same as an implication. But another way of saying it is we have to check all cases. Now, an existential quantifier means that you're just true for some x. So then it is possible to use your other assumptions. I mean, usually such a statement is not in isolation. Using other assumptions, we can choose an x such that px holds. So these often involve two steps. There's a choice, and then there is a check. Check that px is true. These are the two steps of proving that such a claim is true. And these are logically different because here we get to choose it, whereas here we have to fix it. These are logically quite different procedures because in the other case, we can give a formula for it, whatever we want to do. Now, an example of such a condition that involves many of these quantifiers is continuity. F is continuous at x naught if for every epsilon there exists a delta such that if you are close enough, then your function value is close. And this statement really captures everything that we've just said. First of all, this is only talking about only constraining when you are close. To x naught. And it gives you the conclusion that holds when you are close. And another thing about one thing about existential quantifiers that this highlights is that the order of the quantifiers matters in the sense that the choice in the proof of the existential quantifier, it can depend on everything before it. So this delta implicitly is allowed to depend on x naught and on epsilon. And this matters for many proofs, and this leads to other notions such as uniform continuity, and it's good to understand this point to understand the differences between them. Now, the final thing that comes up a lot of the time is negating things. I mean, you want to show that something is continuous, or you want to understand what it means to not be continuous. Well, for proposition, negation is just a statement having the opposite true value, not A, meaning A is not true. So it is false when A is true and true when A is false. But often we're not just negating single propositions, but we are negating a conglomerate of propositions. And we need to be able to negate them properly. And this is where many people make mistakes. So I want to give you clearly that what these negations are, and they are equivalent, meaning that if you compute the truth tables for these on both sides, you will get always the same answers. But some of these are more intuitive than others. If you have not A and B, then this means that either not A or not B. It's enough for one of these to fail to be true in order for A and B to be false. If you're negating an or statement, A or B, then that means that both of these claims have to be false. So not A, not B. And as you notice, there's a certain logic in here that when you go, the connective flips. And the negation signs go in front of the variables. Now, implication is very easy to write this wrong. So I'll write it correctly and then show you that it is actually different than what people often think of it as being. So when is an implication false? That's a crucial thing for thinking about not statements. An implication is false if A holds, so the assumption holds, but the conclusion is false. So the negation holds when A and not B. And I like to say this often as A is true, but B is false. I mean, this is what it is the same thing as saying that A implies B is false. And a quick example. So often people will write, so this is wrong. That if I take not A implies B, not A implies B, there are two mistakes that people make. They write it as not A implies not B. And another thing that people write is A implies not B. And both of these are wrong. Both of these are wrong because let's look at the truth table of these statements. The truth table is for not A implies B. Well, this is true. The implication is true here because A is indeed implying B. The implication is false when A is true but B is not true. And when A is false, then the implication would be true, so the negation forces it to be false. If you compare it to these other statements, then there are differences. They are small, but they are crucial. So if we do the truth table in the first case, what we get, well, A is true, but not B is false. So we would get 0, false. A is true, B is not true. We indeed get correct. But then A is false, so the implication doesn't imply anything, and we get 2 truths. This is different from the table. It does get something correctly, but it doesn't get the full table correctly. So these are not the same statements. And if we have not A implies not B, and it may be easier for many people to do these in intermediate steps, but I just speed this up a little bit. So not A implies not B. Well, when A is true, not A is false. So the implication is automatically true. And then when A is false, then the not negation becomes true. And we have to have B is false in order for the negation to be true. And then we get to the only case where it is false. So this time, the table is even more false because it's false in that claim and it is false in those two. It's false in the one there. So both times we do get 2 of these are correct, but not. And where the mistake is colloquially, I mean, this isn't saying that when A is true, then we get B. This is saying that when not A is true, then not B. But this claim here is saying something quite different. It's saying that A does not imply B. It doesn't say, and the implication doesn't really say anything about the cases when not A is true. So not A can't imply anything else. The implication doesn't depend on the value of not A. And on the other hand, A implies not B will give B a different statement because of these cases when A is false, because the implication is again making no guarantees when A is false, but the other statement is automatically true. So to get not A implies B, the only correct version is what we gave here, is that A is true, but B is false, because that is the case when the implication actually gives you a false answer. Now, the other remaining case is that not for all x, px. That means that if it's not true for all, then there is a counterexample. So there exists an x such that not px. And not there exists means that for every x, not px. So that means that we would have to check every element. So this also is sometimes useful when you're doing proofs by contradiction or contrapositive, is that some of these statements sometimes are easier to prove. It's easier, say, to find one counterexample or find one example. These are often easier to prove than proving for all quantifiers. So what I will end with is giving quick examples of these. So continuity means at x means that for every epsilon positive, there exists a delta positive such that x minus y less than delta implies that fx minus fy is less than epsilon. Well, not that means that the forever quantifier becomes a existence of quantifier. There exists an epsilon such that for every delta, and now we have to negate this implication, and that is, one has to be careful with that, and for that it is easier to put here. It's strictly speaking not needed, it's implied by the context, but for every y as well here. So then we see that exists an epsilon, so for every delta positive, there exists a y such that the assumption is true and the conclusion is false. And these are inequalities, so the conclusion being false means that you are bigger than or equal to epsilon. This is the only correct way to write this, if many other attempts are wrong. Now, another example, and this is in this metric space course very important. We define a set to be open if for every point there exists a delta such that there is a small ball contained inside omega. Well, what does it mean to be not open? This is not the same as closed. Instead, if we say not open, in quantifiers, it means that there exists some point in omega such that no matter the delta that we choose, then not bx delta is a subset of omega. And what does it mean to be not to be a subset? It means that bx delta intersected with omega complement is not empty. It contains points in omega complement. And these points are exactly the points that are on the boundary. And this is why being open is sometimes characterized as not containing any points of its boundary, because a set that is not open is one that contains a boundary point. So I hope you have found this review of these concepts useful, but I will end here.